Welcome back to The Explainer. Today, we're diving right into the heart of data systems, specifically focusing on Chapter 2 of Designing Data-Intensive Applications, Query Languages for Data. We're going to look at how the language we use to actually ask our databases questions fundamentally limits or completely expands what our software can achieve. You know, when you're picking a database, it kind of feels like you're just picking a storage engine, right? But the truth is, you're actually adopting an entire paradigm of communication.
To get us started, listen to this quote from philosopher Ludwig Wittgenstein. "The limits of my language mean the limits of my world." Man, that hits the nail on the head. It perfectly frames our story today. Because, if you think about it, our whole journey as software engineers is really just this relentless quest to hide complexity behind better language. We want to tell our machines what we need, absolutely not how to fetch it byte by byte. So as we trace the history of database languages today, keep this idea in mind. The way you're forced to talk to your database completely defines the boundaries of the problems you can comfortably solve.
All right, Section 1, Imperative versus Declarative Queries. Let's get into it.
Let's establish the absolute core tension in programming. Telling a computer exactly how to do something versus simply telling it what you want. A great analogy for this comes from the web browser world. If you've ever had to manually manipulate a web page imperatively using JavaScript, writing the loops, checking the conditions, applying styles element by painstaking element, you know it is incredibly tedious. You literally have to step through the logic line by line. But on the flip side, using CSS is declarative. You just state your intent. You say, hey, make all these selected paragraphs blue. That's it. You cleanly hide the browser's implementation details. The browser figures out the absolute fastest way to render that blue paragraph, leaving you free to focus on the bigger picture.
Well, believe it or not, this CSS analogy maps perfectly to database history. Back in the 1970s, developers were effectively writing the database equivalent of manual JavaScript. They used things like the codicil network model, where you literally had to write clunky, imperative loops telling the database exactly which paths to traverse just to find a simple record. But then came the beautiful, declarative SQL revolution, rooted in relational algebra. Suddenly, you didn't need to loop through records anymore. You just declared the pattern of the data you wanted, and the database did the rest of the heavy lifting.
And this is exactly why declarative won out in a massive way. It frees you from micromanaging your database. Because the declarative query like SQL only specifies the end goal, it hides all those messy implementation details of the database engine. This means the query optimizer can do what it does best. It looks at your request, checks its indexes, and decides on the absolute best execution strategy right there on the fly. Plus, because you aren't dictating the exact sequential order of operations, the database can automatically parallelize that work across modern multi-core CPUs. You're basically getting performance upgrades for free just by upgrading your hardware without ever rewriting your queries. How cool is that?
Moving right along to Section 2, the MapReduce middle ground.
So the crucial thing to understand here is that not every database system stayed purely declarative. As the web exploded in scale, systems had to handle massive distributed datasets, and they desperately needed a different way to query. Enter MapReduce. Popularized by Google and quickly picked up by NoSQL data stores like MongoDB, MapReduce is a programming model designed for crunching enormous amounts of data in bulk across entire clusters of machines. It sits in this slightly awkward but incredibly powerful middle ground between declarative SQL and full imperative code. Instead of one declarative statement, it executes user-defined JavaScript snippets across a distributed system.
Let's break down how this distributed computing concept actually works step by step using a really fun example from our sources about ocean observations. Say we want to count shark sightings per month. Okay, step 1, we filter our massive database for just our target, sharks. Step 2, we run a map function. This is just a piece of custom JavaScript that looks at every single shark record, extracts the relevant time data, and emits a key value pair of the year, month, and the number of animals. And then finally, step 3, we run a reduce function. This takes all those pairs we just grouped by month and simply sums up the total observations. You're writing imperative code, sure, but the framework itself handles all the crazy distributed execution behind the scenes.
But wait, here's the plot twist. It turns out writing 2 carefully coordinated JavaScript functions for every single simple query was just way too painful for developers. MapReduce is super powerful for sure, but it's a really low-level way to ask questions. So what happened? NoSQL databases like MongoDB essentially ended up reinventing declarative SQL. They created the JSON-based aggregation pipeline. It's a declarative query language that just looks like JSON instead of English, basically proving that for everyday data retrieval, the declarative paradigm is just incredibly hard to beat.
Which brings us to Section 3, querying the graph.
Okay, so this is where the mighty declarative SQL we've been praising the whole time suddenly becomes the villain of our story. Imagine a property graph that visually maps out a network of relationships. We've got a person named Lucy, born in Idaho, and Alain, born in France. They're married, and they both currently live in London. Now, in a traditional relational database, modeling this would be a tangled nightmare of foreign keys and join tables. But in a graph model, the vertices, meaning the entities, and the edges, their relationships, are treated as first-class citizens.
Let's say we want to query this graph to find people who emigrated from the US to Europe. To do this, we'd use a language like Cypher. Cypher is our sleek, declarative hero for property graphs. It can pull off this complex relational search in literally 4 elegant lines of pattern-matching code. You actually draw ASCII art arrows right in your code to represent the relationships you want the database to find. It's incredibly readable and tells the optimizer exactly what pattern it needs to hunt down.
Now brace yourself. In stark contrast, if you try to traverse those exact same variable-length paths in a standard relational database using SQL, you have to use something called a recursive common table expression. And let me tell you, that takes a clumsy, painful 29 lines of dense, hard-to-read code just to ask the exact same question. When your data is highly connected like this, the rigid tabular structure of SQL becomes a massive limitation on your language, and therefore a limitation on your world.
Now, you might be thinking, wait a minute, isn't this interconnected node stuff just the 1970s Codacil network model in disguise? Actually, no. Modern graphs are fundamentally different. They absolutely do not restrict your schemas. Any vertex can connect to any other. You can jump directly to any vertex ID without having to traverse some rigid access path. The vertices are unordered, and honestly, the most important part is that graph databases use these beautiful high-level declarative languages like Cypher or Sparkle instead of the brittle, imperative code of the past.
And that leads us to our final part, Section 4, the Data Log Foundation.
To wrap things up, we're actually going back in time a bit to look at the academic grandfather of all these graph query languages. Used in modern systems like Datomic, Datalog is actually a subset of the logic programming language Prolog. It takes a completely different approach. Instead of thinking in terms of tables or interconnected property nodes, data is framed purely as predicates. You just write it out, predicate, followed by a subject and an object. By defining these basic facts and then defining rules based on those facts, you empower the database to build up immense complexity, one logical step at a time.
So Datalog basically applies these logical rules recursively to derive entirely new facts that were never explicitly stored in the database in the first place. For example, the system can logically deduce that because Idaho is within the USA and the USA is within North America, well, Idaho must be within North America. It requires a totally different mental model compared to SQL or Cypher, but it is just incredibly powerful for complex, highly connected data, where you really need the database to act almost like a smart inference engine.
So, I want to leave you with this final, provocative thought. As we've seen today, from the tedious imperative JavaScript to the magic of declarative SQL to the MapReduce middle ground and the elegant patterns of Cypher and Datalog, when you choose a database, you aren't just choosing a storage engine. You are choosing a language. You're choosing the very vocabulary you'll use to solve your hardest problems. So take a hard look at the systems you're building today and ask yourself, what limits is your current language placing on your world? Thanks so much for joining me for this explainer, and I hope you're walking away with a totally fresh perspective on the true power of query languages.